Hi, good morning everybody. So today we have come to our fourth lecture on rate processes. So we were discussing the effect of temperature on reaction rates. Okay, so we will continue to this, that is we will give a little detailed account on this. So let us start. So with respect to reaction condition, temperature is a very important factor that controls the chemical reaction. Okay, apart from temperature, pressure, concentration, catalyst, solvent, these are also important, but temperature is also a very important parameter, and that if we change temperature, reaction rate is found to get affected, and if you increase the temperature, generally what happens is reaction rate increases. You don't ever find that the reaction rate is decreased. Okay. So it has been observed that in means it is basically a recapitulation of some parts we already have talked about. It has been observed that in homogeneous thermal reactions, thermal reaction means the reactions which occur just by applying heat from outside. Homogeneous means it happens in one phase, okay, not in two phases or multi phases. For homogeneous thermal reactions, for every 10° rise in temperature, the rate constant is doubled or even tripled. The ratio of rate constants at two different temperatures separated by 10° centigrade is called the temperature coefficient of the reaction, and mathematically this temperature coefficient is nothing but K at T plus 10 by K T, and this is found to be of the means close to 2 to 3, okay, and this is for homogeneous thermal reactions, in other cases something else may happen with respect to Kt plus 10 by Kt. Okay. So the first mathematical relation between rate constant and absolute temperature was given by Hood in 1878 as follows, that is ln K is equal to A minus B by T. You see that it is an empirical relation that says that if you plot, as I told you, as I talked about in previous lecture, that ln K versus 1 upon T will be giving you a linear slope. So here also this is a similar relation, and it is prior to, it is before Arrhenius proposed his equation, his famous equation. So A and B, these are constant quantities for a reaction system. The values of A and B, these may be obtained by plotting ln K versus 1 upon T, that is from slope you will be getting B, and from intercept you will be getting A. Now this Hood's equation, this equation was based on the experimental result, that is from the experience that means whatever data or whatever results people have gathered out of various chemical processes, that is found to fit in this equation. So it is basically based on experimental results, that is based on experience. So some theoretical significance to this equation was given by Van 't Hoff in 1884 on the basis of the effect of temperature on equilibrium constant. So Van 't Hoff tried to give some idea why this happens. Okay. On the basis of effect of temperature on chemical equilibrium constant. So, equilibrium constants are very sensitive to temperature. So, if you change the temperature, equilibrium constant will also change. So, based on that, since equilibrium constants are affected, so he tried to explain on the basis of this observation. This idea was further extended by Arrhenius in his attempt to obtain the relation between rate constant and temperature. The relation obtained was then successfully applied by him to the effect of temperature data for a number of reactions, for a number of chemical processes, and the equation is usually called the Arrhenius equation, which is ln k is equal to A into exponential, it is not ln k, k is equal to A into exponential minus EA by RT. So, if you take ln k is equal to ln A minus EA by RT. So, these two are very similar. So, this A is similar to ln A and this one is similar to this. Okay. So, actually Arrhenius, from the idea of Hood's equation, he gave this new expression, that is k is equal to A into e to the power minus x EA by RT, and that has been found to fit very well with chemical systems when temperature is modified. So, Arrhenius equation consider a general reaction that A is converted to B, and say energy of A is EA and energy of B is EB. So, like this, A to B. So, it is K1 reverse is K minus 1, and energy is EA, this is EB. Okay. So, concentration equilibrium constant, which is K1 by K minus 1. So, what Van 't Hoff tried to explain is like this, based on his idea on effect of temperature on equilibrium constant, that ddt of ln Kc is equal to delta E by RT square, where delta E is nothing but EB minus EA, that is final minus initial, that is the energy change associated with this process of transformation from A to B. So, it is merely the energy change associated with this chemical transformation. Okay. So, he tried to use this expression and with the idea that A with EA, B with EB. So, the difference in energy will be EB minus EA, and then he has plugged in this value to this one, to this expression. Okay. So, if we write, if we plug in this onto here, then what do we get? ddt of ln K1 by K minus 1, which is equal to delta E. Delta E means basically EB minus EA by RT square. Okay. So, if we split this, so basically delta E is nothing but EB minus EA. Okay. Either you can write delta E or maybe EB minus EA in this way. I am just writing this together, means this one is nothing but this one, delta E means this one. So, if we now split this expression into two equations, then this will look like ddt of ln K1, that is rate constant for the forward process. Okay. So, basically we started with this A to be forward rate and backward rate. So, ddt of ln k1 is equal to Ea by RT square plus some constant z. This is the first equation. The second equation is ddt of ln k minus 1 is equal to Eb by RT square plus z. So, for any general reaction, what do you get? Suppose we have a general reaction like A to product with a rate constant K with energy E, then we write using this Arrhenius equation ddt of ln K is equal to E by RT square plus Z. So, basically this has the form, this particular in a general form. So, this has the form like K is equal to A into exponential minus E by RT square. This has the form, not exactly the, this is not the exactly the energy of activation, but this has the form that rate constant has got some pre-exponential term, and within exponential there must be an energy term. Sorry, this is RT. There must be an energy term within this exponential. Okay. So, this way this Arrhenius equation arrived into. Now, again what is this E, or for your Arrhenius equation K is equal to A into exponential to the power minus Ea by RT. So, what is this Ea? Let us refer to this slide, that this is the slide, let us look into that, this is your reactant initial state. It is a starting point of your reaction. Okay. Then what happens, an activated state is formed, which may be called as an activated complex, and then this activated complex or activated state is transformed to product. Okay. So, it is now then transformed to this product. Okay. So, the difference in energy state between the reactant, that is the initial state, and the activated complex is called the activation energy for the forward process. So, this is your reactant or initial state, this is your activated state, and say this is your product state. Say this is your products, that is your final. Okay. So, difference in energy of these two, okay, difference in energy of these two, it is called the activation energy for transformation from reactant to activated state. So, like this. So, it is the forward process, forward activation energy. In the same way, this difference is the difference between the activated state and the product state, and basically if you draw an arrow like this, so it is for the backward or reverse process. So, it is called the activation energy for the reverse process. So, this is forward activation process, forward activation energy, and this is your reverse activation energy. Okay. And you see here I have drawn the reactant state and the product state in such a way that product is above reactant state. Okay. So, that means what is happening, that moving from here to here, your energy state of the whole energy of the system is increasing. So, that means it is energy extracting, that is energy is taken up from outside. So, it is not energy generating, it is not an exothermic process. Suppose if your product state is here, then it is lower in energy. So, it is if primed, it is lower in energy compared to a reactant. So, that means this much of energy would have been released. Therefore, this process would have been an exothermic process. And so, difference between these two, either this or maybe these two pairs, it is called the heat of reaction, that is the energy, I mean enthalpy difference between this and that. Okay. So, it is higher heat H value, this is lower H. So, that means energy to be taken up, and this is lower H, this is higher H. So, energy will be released. Okay. So, that means reactant, activated state, then product, and then the relative position in energy scale will determine whether the reaction will be exothermic or the reaction will be endothermic in nature. Now, let us move on to one example, that dissociation of HI, okay, at two different temperatures. So, let us look into this process 2 HI giving rise to H2 plus I2 in gas phase. So, rate constants are given to be 3 into 10 to the power minus 5, another is 2.5 into 10 to the power of minus 3, that it is increasing. This is at 620 Kelvin and this is at 730 Kelvin. Remember that as you increase the temperature, rate constant is increased, like that thumb rule, that for every 10 degree rise of temperature, the rate constant is increased by 2 to 3 times. Of course, that is for homogeneous thermal reactions. And given that delta H for this process, is 15.5 kilojoule mole inverse. Okay. So, we have to find out the activation energy for forward and backward reactions. So, E act forward and also E act activation or EA, whatever you say, backward, is how much, that we have to find out. Okay. So, so how to do that? Now, first we have to use, since we are means this rate constants are given for the forward processes. Okay. So, we have to make use of this Arrhenius equation to find out the activation energy of the forward process, and then with the help of that diagram that I already have shown, that this is your activated state, say this is your forward activation energy. So, EAF say, and say this is your backward reaction activation energy EAB, and this much is your delta H. So, basically delta H is equal to EA forward minus EA backward. So, we have to make use of this equation to find out this backward activation energy, I mean activation energy for the back reaction. So, let us first find out the forward activation energy. So, it is given like this, that ln K1 by K2 or K2 by K1 is activation energy by 8.314 into 1 by 2 different temperatures. One, this is your initial temperature, this is your final temperature. Okay. So, upon calculation, if you simplify, then activation energy for the forward process will be coming out to be 185 kilojoule per mole. So, just making use of your this Arrhenius equation, you can find out the forward activation energy and then you make use of this equation, that delta H is equal to E activation forward minus E activation backward, since you know E activation forward. So, backward activation, I mean activation energy for the back process will be found from this one, and this comes out to be this. So, backward activation energy is less. Okay. So, it is an endothermic process. You see the sign is plus, it is an endothermic process. Okay. So, this way you can find out activation energy for the backward, I mean back reaction and the forward reaction, provided you are given delta H of reaction. Next, another problem, prove that for an nth order reaction, the plot of T half versus 1 upon T is a straight line and the slope of the line is equal to activation energy. Okay. So, we know ln k versus 1 upon T, if we do a plot which is typical Arrhenius using Arrhenius equation, then slope will be giving you activation energy, I mean EA by R. Okay. But here for an nth order reaction, you have to prove that ln T half versus 1 upon T is a straight line with slope equal to E act. So, we have to start with this one, that ln k is equal to ln A minus EA by RT. This is your Arrhenius equation, and T half for the nth order reaction is given by this. This is your initial concentration. Okay. So, this is I already have talked about the expression for T half for nth order reaction. Of course, in this case n must not be equal to 1, that you have to remember. Okay. So, if you take logarithm, that is natural logarithm ln both the sides, then you will be getting this expression. Okay. Then what you have to do, you have to plug in, I mean you have to replace ln k by this, ln k is equal to ln A minus EA by RT. So, you write this in place of ln k, ln A plus EA by RT. So, this is a constant quantity. You see, the ln A is a constant as long as temperature is fixed, and the reaction, I mean you are talking about a particular reaction. So, this is a constant. So, you see that ln T half is equal to EA by RT. So, so slope basically EA by R. Okay. So, slope is nothing but from slope you will be getting EA. So, for a typical nth order reaction n is not equal to 1, you can prove that T half versus 1 upon T will be giving you activation energy. Okay. So, this way you can show this one, and of course, this is a straight line, because you see ln T half is equal to constant plus EA by RT. So, T half versus 1 upon T is a straight line. Another example, for a second order reaction, the reaction rate constant at 3 degrees Celsius was found to be 8.9 into 10 to the power minus 3 liter mole inverse, and 7.1 into 10 to the power minus 2 liter mole inverse at 35 degrees centigrade. So, find the activation energy. So, it is a straightforward. Basically, we use this expression ln k2 by k1 is EA by R into this one, and upon plug in the respective numbers, you will be getting EA, which is equal to 45.9 kilojoule mole inverse. Next, what is the significance of temperature coefficient? So, temperature coefficient significance means T, I mean kT plus 10 divided by kT, which is equal to 2 to 3, means as you increase the temperature, reaction rate increases, rate constant is getting raised from a particular value. Okay. So, that is the significance, that is the typical signature of a chemical reaction, that if you increase the temperature, your reaction rate is enhanced. Next is energy of activation. What is energy of activation? Now, as I told you that in order to form an activated state, some energy is needed, and next is why activated complex is needed? Because you need to cross a barrier, otherwise you cannot reach your product state. If you are in a reactant state, say this is your reactant state, say this is your product state, you cannot directly move from here to here. There is a barrier like this. You must cross it, otherwise you cannot go directly. Okay. So, this barrier is called the activation barrier, that you must cross. So, this is EA, you must cross the barrier, and this is the progress of reaction. Progress of reaction, or may be called as a reaction coordinate. So, you must cross the barrier. So, this much of energy must be supplied from outside in order that the reactant is crossing can cross the barrier. Okay. So, this much of energy must be supplied, must be needed, otherwise reaction will not take place. Arrhenius factor, that is K is equal to A exponential minus EA by RT. So, this is your Arrhenius factor. It is also called as the frequency factor. So, this is called the Arrhenius factor, and this is your exponential term. What is an activated complex? Activated complex is basically a state, or activated state is the state which is here. It is high in energy. High in energy means either reactant or product, these two are lower in energy compared to this activated state. Okay. So, this is high in energy compared to reactant state or product state. Now, this activated complex is formed in various ways. It may be formed in various ways. Now, the point is according to latest theories of reaction rates, which we will discuss later time, that suppose if it is a homogeneous gas phase reaction, then you have got reactant, say reactant A and say another reactant B. So, what is needed is that, so A and B should come close to each other. Okay. Otherwise, suppose there is required an atom transfer from say A to B to give your product B. So, that means they must be close to each other, or they must be in vicinity of each other, so that this atom transfer can take place. That means only possibility in gas phase is that if there is a collision, then they can come close to each other. So, basically by means of collision they can form a momentary complex which may be regarded as an activated complex. Then this activated complex, once it is formed, then it has got the option, either it can go in this direction which explains the back reaction, or maybe it can go, it can cross the barrier and go to the right hand side, which explains the product formation. This explains your again back reaction. Okay. So, that means this activated complex formation is a very important thing, and it needs to be further discussed. So, we will discuss this point later on, means what is activated complex, how does it look, and what are the factors that that can affect the relative energy state of this activated complex, that we will discuss, and what is the effect of temperature and how temperature alters this activated complex formation, whether it is expediting or something else. We will talk about maybe later time. Okay. So, A plus B producing product. So, it is a simple gas phase reaction, it is a kind of collision. Okay. So, it is a collision reaction, maybe reaction all reactions are not gas phase reactions. So, in solution phase something else may happen. Next is we must talk a little about catalyst. What is a catalyst? Now, because since I started to talk about although in brief, but I started to talk about this activated complex and a possible geometry of the activated complex. Possible geometry maybe say by means of a hydrogen bond formation. Say we have got one entity and there is a hydrogen which is just projected out, and there is another entity, suppose there is a nitrogen. So, in the gas phase there is a possibility of say hydrogen bond formation. So, this hydrogen bonded complex sometime can be an activated complex, and then later on after after if we give more time, then this hydrogen will maybe get maybe transferred from here to here, producing your product. So, that will come later on, but the thing is there is a definitive role of catalyst in speeding up the reaction. Okay. Now, what is a catalyst? Catalyst is a substance that increases the rate of a chemical reaction without itself being destroyed or used up. In this particular discussion, we are not taking up catalyst in detail, but basic understanding what does a catalyst do for a chemical reaction. We just try to understand that. Okay, so you have this Arrhenius equation, K is equal to A exponential minus EA by RT, where EA is the activation energy and this is your absolute temperature, and so A plus B producing C plus D. So, this is your activation energy EA. Suppose and EA, so if EA is more, the barrier crossing rate will be less. So, as I told you in earlier lecture that if activation energy is more, then reaction is generally slowed down. I mean slow reaction, it is a result is a slow reaction, although temperature effect is more, but it is a slow reaction. When activation energy is less, then reaction is fast. So, suppose by a specific means or by some means, if we can reduce this EA, maybe by introduction of a third component in the reaction mixture, or maybe by some other means, maybe if we raise the energy state by some means, or maybe if we reduce the activated state by some means, then this separation will be reduced, this separation will be reduced. So, if this separation will be reduced, then possibility of barrier crossing from here to here, producing your product, that is the progress of reaction, will be more. Okay, that means lowering of activation energy will lead to an increase in rate constant. Okay. So, if this is an uncatalyzed reaction, and suppose in presence of catalyst, if this happens, like your activation energy is reduced, then your rate will be further increased. Okay. So, then what is the role of a catalyst? So, basically catalyst provides an alternative path that demands lesser activation energy. You see, this is a path, this is also a path producing A plus B to C plus D, giving from A plus B to C plus D, but it is an alternative path. Why I am saying alternative path? Because it demands less of activation energy, EA primed, where EA primed is less than EA. So, it offers an alternate path with less of activation energy. Okay. So, that means rate of a catalyzed reaction will be more than the same reaction when it is under not catalyzed condition, uncatalyzed condition. So, in that case EA catalyzed is less than EA uncatalyzed. Next is you see here, this is the energy level diagram. So, activation energy is this is x y, EA x y, x to y, and this is activation energy for EA y to x. Okay. So, you see that the black one, the black line, so it is having higher activation energy. You see EA x to y, it is the normal reaction, uncatalyzed, higher activation energy, and also for the backward process it is higher. Okay, this one is higher. Okay, but the red one is the catalyzed one. In presence of catalyst, you see the forward activation energy EA primed XY. You may call this as EA primed XY or EA catalyzed XY. It is less, and also EA catalyzed YX, it is also less. So, you see that in both the direction, for both the direction, I mean forward or backward, in both the direction, you know, your activation energy is reduced. That means lower activation energy means your faster reaction. So, faster in both the direction. Okay. Faster in both the direction means equilibrium is reached quickly compared to uncatalyzed reaction. Although you see delta H for the process is not altered, but only thing is that it provides, that is catalyst provides an alternative path demanding less activation energy for both the direction. Okay. So, that is why catalyzed reactions are faster, okay, because it demands less activation energy, and this is a reaction path in this direction. Okay. So, in heterogeneous catalysis, heterogeneous catalysis, catalyst can be homogeneous, catalyst can be heterogeneous. So, in homogeneous case, catalyst and your reactant both are in single phase or same phase, and in heterogeneous catalysis what is happening, that the reactant and the catalyst are in different phases. Maybe one is in liquid phase, another is in solid phase, or maybe one is in solid phase, another is in gas phase. So, typical example is Haber synthesis of ammonia. Okay. N2 plus 3H2 is equal to 2 NH3. It is a Haber synthesis of ammonia. So, here the catalysis occurs, in a heterogeneous fashion. Also, Oswald process of production of nitric acid. Here also, this is an example of heterogeneous catalysis. Homogeneous catalysis, there is, in this case, reactant and catalyst are dispersed in single phase, usually liquid, and typical example is acid base catalysis, like say ester hydrolysis. Say ester producing acid plus alcohol. It may be catalyzed by H plus or OH minus. So, maybe you add a little amount of say HCl or maybe little amount of NaOH. So, organic ester will be hydrolyzed to produce acid and alcohol. Of course, in presence of OH minus, acid will be corresponding salt. So, it is a case of homogeneous catalysis. Okay. So, if you do not add H plus or OH minus, the reaction happens, but it is a very slow reaction. Okay. Now, enzyme catalysis is another example. It is a biological catalysis. Okay. I talked about heterogeneous catalysis or homogeneous catalysis. All these are non-biological processes, but for biological cases, it has got a different name, which is called the enzyme catalysis. Enzymes are small proteins or polypeptides. So, they tend to form a complex, like which is called the enzyme substrate complex, okay, with the substrate, and then this substrate will proceed to this enzyme substrate complex will proceed towards the forward direction, giving rise to the product, and then what happens, this enzyme is retained back. Okay. So, it is a typical biological catalysis. So, this biological catalysis part will be taken up in appropriate section, appropriate lecture. So, let us have a look at this Haber ammonia synthesis. So, it happens normally, since nitrogen is having a triple bond N plus H2. So, this is very unreactive. We have plenty of nitrogen in atmosphere, but they are not reactive, and this nitrogen, so unreactive nitrogen undergoes this reaction, N2 plus 3H2 producing 2NH3 ammonia production, and it requires catalyst, iron catalyst, and in presence of these are called promoters. So, in presence of promoter iron catalyst, and of course, it is a huge temperature 450 degrees centigrade and about 200 atmospheric pressure. So, it is a very high pressure and of course, high temperature. So, at elevated temperature and pressure condition, what is happening, that this nitrogen hydrogen combines to form 2NH3. So, this iron in K2O, calcium oxide, and Al2O3, these are in solid phase, okay, and at a very high temperature, and of course, this nitrogen and hydrogen, they are reacted at a high pressure, high atmosphere, I mean external pressure is very high, okay. So, it is a case of heterogeneous catalysis, okay, because if you do not put these conditions, then the reaction does not occur, and this has got a tremendous industrial application, that just you have got this nitrogen, enormous amount of nitrogen you can get from atmosphere. There is virtually no expenditure, just you have to supply hydrogen, and then this is regenerated. Since it is a catalyst, it is regenerated, okay. So, it is regenerated means recycled. After one complete cycle, it is recycled back to your reaction chamber, and then again this process occurs to give you ammonia. So, in presence of this catalyst, this reaction at this temperature pressure condition, it gets facilitated. So, catalyst has got an immense role in industrial preparation. There is another example, Oswald process for the preparation of nitric acid. So, it is at 900 degrees centigrade and pressure is 4 to 10 atmosphere. It is also a bit high pressure, okay. So, in presence of platinum rhodium catalyst, this ammonia combines with oxygen to produce NO, nitric oxide. Then nitric oxide again in presence of oxygen produces nitrogen dioxide. Then nitrogen dioxide reacts with, dissolves in water to produce HNO2 and HNO3, okay. So, equated form of your nitric acid, and then this nitric acid is further processed to give you the further process to get you nitric acid, this HNO3 aqueous, because it is a dilute situation. So, you have to concentrate it. So, you see that 900 degree centigrade 4 to 10 atmosphere in presence of platinum rhodium catalyst. If you do not give it, again it is a problem, you do not get this one. So, this in presence of catalyst, this reaction means under this condition, this reaction occurs to produce nitric oxide and further reactions. So, catalysts are having tremendous importance in chemical processes. Now, next is let us have a very simplistic description of enzyme catalysis. So, enzyme is a macromolecule like this, and it has got certain pockets, okay, and in this pocket the substrate, okay, substrate forms. So, this is your enzyme, so this is your substrate. So, it binds to produce an enzyme substrate complex, ES complex. Normally substrate giving rise to product. So, it requires maybe like this much of energy of activation, but the moment enzyme comes into picture, then maybe say this is your enzyme substrate complex, then enzyme substrate complex maybe with it is giving rise to like this, okay. So, enzyme substrate complex, then another state maybe is there after enzyme substrate, it is further and converted to another species, and then it gives rise to a product, okay. So, why this is like this, I will come to that point later on, but I am just trying to give you some idea. So, you see this much of gain in activation energy. So, activation energy has been reduced this much, therefore, reaction is faster. And also another important point is that enzyme catalyzed reaction has got some, if you plot rate versus temperature, you will be seeing that it has got some optimum temperature. Okay. Below this temperature, this process is not very much facile, and also above this temperature, when temperature is high, this is also reduced, because of the fact that these biomolecules, these are very temperature sensitive. So, at an elevated temperature, their specific structure which is responsible for such enzyme substrate complexation is lost because of high temperature or increase of temperature. This coiled structure, because protein has got coiled structure in a 3-dimensional sense, it has got a coiled structure. Okay. So, it has got a folded structure. It is a long polymeric system. I mean, it has got amino acid residue, many amino acid residues, and they form a coiled structure, or maybe it is a folded structure. So, if you increase the temperature, maybe this portion, the active site, which is called the active site, is misfolded or maybe unfolded, so that this enzyme substrate complexation is no longer facile, and as a result of which this lowering in enzyme substrate this activation energy is not there, and as a result of which the reaction rate is reduced. So, enzyme substrate reaction is a special case of where it is also called as biocatalysis. So, I will talk to this biocatalysis in more detail, maybe in appropriate class, but I just have given you an idea what is this biocatalysis. So, basically the role of this enzyme is that it is regenerated. So, enzyme then plus substrate producing enzyme substrate complex, then it is producing product plus enzyme back, then again this enzyme is recycled, I mean then again next substrate molecule producing the same thing. Okay. So, it is recycled. Okay. The small molecule, small maybe it is a typical maybe 100, 200 or maybe 50 amino acid residue containing protein molecule. So, it will be regenerated after the reaction. Okay. So, this is enzyme substrate enzyme catalyzed reaction, and I just told you this heterogeneous catalysis, and also I gave you the idea of this homogeneous catalysis. And homogeneous catalysis has some more features which I will talk about. Like features means, say if you have suppose you have got hydrolysis reaction, acid catalyzed hydrolysis reaction, that is your ester producing your acid plus alcohol. Okay. So, rate will be, suppose it is, if it is a first order reaction, then rate is equal to K into your concentration of ester, and of course CH plus is there. CH plus is there means if hydrogen ion concentration is double, then your rate is double. It is a simple 1-to-1 correspondence. So, basically this CH plus including this is producing, giving you KCH plus into ester. So, if you increase your CH plus concentration to double, then your rate will be doubled. So, if you just divide the old rate with the new rate, then you can find out how many fold you have, how many fold increase of H plus has been made. So, this is basically called, your CH plus is called the catalytic coefficient. Okay, so there is a 1-to-1 correspondence between this. So that's why it is called the homogeneous catalysis. That is, if you increase your catalyst concentration by a factor of 2, your rate will be increased by a factor of 2. Okay, so and this part I may be in a separate lecture where I will talk about this catalysis. So these aspects will be taken up. Okay, so what we have learned in this concluding section of effect of temperature on chemical reaction, that Hood was the person in 1878 gave the idea that lnk has got an inverse temperature dependence. Okay. So, that is lnk is equal to A minus B by T, and from that, using the idea of Van 't Hoff, Arrhenius put forward his famous equation. Okay. And his famous equation, from his famous equation, I mean Arrhenius' equation, we can find out the activation energy for the chemical reaction by doing some temperature variation experiment. I already talked about it in last class, that how to do, you know, this, how to find out activation energy. That is, you have to carry out the reaction at different temperatures, maybe at 3 different temperatures. Okay. And then in these 3 different temperatures, you find out rate constant. Okay. You find out the rate constant and then plot logarithm of that found rate constant as a function of 1 upon T, and from slope and intercept you find out the respective quantities like E activation, that is activation energy, and you know, frequency factor. And we have done a number of, you know, certain examples, and then we also have talked about the significance of temperature coefficient, energy of activation, which is very important parameter, which is a very important factor, Arrhenius factor, and also the what is you know, grossly meant by the term activated complex. Activated complex means it is basically an activated state, and it is a kind of complex formation in the activated state. That is, it is a higher energy state, and that higher energy state will eventually be transformed to either the product side or maybe to the reactant side. So, if it is crossing the barrier if it goes to the right hand side, means a product formation, and if it comes back, means it is, you know, back reaction. That is, I talked about you know, reversible reaction. So, it explains reversibility also. Then I give you a very short introduction of catalyst. What is a catalyst? That catalyst is a substance which provides an alternate path, that is the path which demands lower activation energy, or you can say that it lowers the activation energy by providing an alternate path. And also we discussed you know, with 2 examples. One is Haber synthesis of ammonia, where these are the example of heterogeneous catalysis, that is, catalyst is in a different phase than your reactant and product. And homogeneous catalysis we also talked about, that is, you know, catalyst, reactants and products, all these are in the same phase, single phase, that is why it is called the homogeneous catalysis. We also give a very brief introduction of enzyme catalysis, which is nothing but a biocatalysis. Okay. And so in the next class, what should we take up? Let us again go back to maybe to the first slide, that we will move on to complex reaction. We just started with this back reaction, maybe parallel reaction, but we have not given a complete account of them. So in the next class, in the next lecture, we will talk on complex reactions, where we will, you know, take up this parallel reaction, sequential reaction, reversible reaction, and many other aspects. So, till then, have nice time. Thank you.